Hello and welcome to another episode of Rustacean Station. I'm your host, Alan Wyma, and today I have Adi, who is the Director of Product at Informal Systems. Adi, maybe you can do a quick introduction of yourself because I didn't mention your last names, but I'll let you go ahead and introduce yourself.
Yeah, no worries about pronouncing the family name. It has Polish origins, Seredinsky for reference. So originally I come from Romania, but as I said, the name is originally Polish. It used to be written a bit differently, but then it got adapted to Romania. And currently I'm with Informal Systems. We are a cooperative. We're building a lot of core infrastructure, basically distributed systems, but we also focus on formal verification, security audits. We also operate infrastructure. And here I serve as a director of product. I've been with the company since it was created in 2020. So it's been more than 5 years now. And I think that covers a bit my brief background of myself.
It's also good to understand a little bit more about because you're a director of product, right? So I'm guessing you probably have been working for some time. I mean, you didn't just graduate and start as a director of product, right? Because it sounds pretty high up as a director. So within the last few years, I mean, what were you kind of working on before you got to Informal Systems? Or have you just been there and just kept going up the ladder?
Well, within the company, I did change a lot the kind of activities and my role actually throughout the years. Maybe this is a good kind of introduction to the kind of work that we do in a bit more specifics. So when I joined, I was actually a researcher. I think my official title was research engineer, if I recall correctly. I was just fresh out of a PhD program at EPFL in Lausanne, Switzerland, and throughout that PhD program, that took me 6 years, I was actually working on consensus algorithms, in particular consensus algorithms for Byzantine fault tolerance. And that's a subset of, let's say, distributed systems area that became quite hot, let's say. It was definitely rejuvenated because it used to be considered a bit of a more niche area or almost dead. It was first rejuvenated by some interest from various big companies that were just spinning up their cloud services. So in particular, Google, for instance, is one, but Yahoo as well had some really interesting research in distributed systems and in particular in consensus. And then when Bitcoin came up, a lot of people were just suddenly realized, oh, actually what Bitcoin is doing is this thing that researchers in distributed computing and distributed systems have been, researching for 40 years. And Bitcoin solves the same problem, the BFT consensus problem. BFT stands for Byzantine fault tolerance. And that's what I did during the graduate school. I finished in 2019, and then I joined Informal to work as a researcher. It was almost quite a continuation of what I had done before, in the sense that I continued to do experiments and to improve the performance of distributed systems, and in particular, one particular distributed system that was an implementation of a BFT consensus algorithm that is called Tendermint. So that's how I joined the company, and that's what I did initially. Throughout the years, I pivoted multiple times and got my hands involved in various other parts besides just consensus. In particular, there was a time when I was involved a lot in a domain that is called generally interoperability, and this has to do with how do you make different distributed systems communicate with one another reliably. And furthermore, if those distributed systems are made so that they have each Byzantine fault tolerance guarantees, that's what the blockchain is essentially. It's a Byzantine fault tolerant distributed system, such as Bitcoin or Ethereum. How do you get one of these systems to trust that another one of those systems did something? For instance, I give you money on one of these platforms. I transfer maybe 50 francs to Alan. How can I convince, and I do that on a certain platform, it could be Ethereum. How do I convince my account on Ethereum that I have done that transaction to Alan of 50 francs? And that's called interoperability. I did that for a few years as well. There is a very interesting protocol that we have helped create, design, verify using formal methods, debug, and then implement in Rust, and then deploy and operate throughout the years. The protocol and the system name is called IBC, or Inter-Blockchain Communication. It still exists, and it's very interesting piece of work that we're very proud of. And these days, I am back into consensus land, so I no longer am focused that much on interoperability. I still work in Rust, and I'm back into consensus land, specifically working on a system that we call Malachite. And this is also an implementation of Tendermint. So if you recall, that's what I said I worked on originally as a research engineer, except Tendermint used to be written in Go. It was a bit tough to evolve as a very, very complex system. It was extremely entangled, super reliable, actually. It's probably still is the gold standard in terms of reliability, but it has a bit ossified because it was extremely difficult to evolve and to add new features and so on. So we decided to rebuild this protocol called Tendermint. We rebuilt it in Rust, and that's what became Malachite. And it's a flagship project in Informal systems, and that's actually my main area of focus these days. Yeah, that's a bit of a odyssey.
I mean, that was quite a history you gave us, but let me try to recall and see where we can start to kind of break this thing down, though. But I mean, since we are a Rust podcast, and this is definitely something I can definitely chime in on, is the part about going from Go to Rust. I mean, I've heard this story so many times. I think there is some times where people actually go from Rust to Go, but I feel like that's less. But I would like to talk a little bit about switching platforms, and maybe it would be good to first say why was it written in Go to begin with? What challenges were there that Go was giving you, and how did Rust help to solve those kinds of challenges? Because I'm guessing there was probably at least a technical problem, and you definitely mentioned that there was like I forgot how you called it, but I feel like it was an issue of it's hard to expand. Is that what I think you actually said something like that? Mate, go ahead.
Yeah, that's a pretty deep topic that we could go into. I guess if I was to start at a high level, just before going into the technical details, we are very focused in the company in Informal in what we specialize in is security and highly reliable systems, building, verifying them, and operating them. The ultimate mission is to foster trust in software. We also qualify it as fostering trust in money, which is a kind of a different conversation, which maybe explains a bit why we were, from the beginning, we were a bit biased on Rust. Actually, I recall in 2019 when I met the rest of the gang, I was pitched with a vision for the company that it will have two pillars. One of them was formal methods, specifically TLA plus for the people in your audience that are into distributed systems and distributed computing. And the other pillar besides formal methods was Rust, actually. And the idea was, well, we have been building all of this crazy infrastructure for money and for value on internet, basically digital cash and so on. But how safe and reliable are this? Are we ourselves willing to trust them and to use them? And are we willing to trust that the whole rails for finance and so on is going to be stable and reliable? And we said, well, it's a very difficult question, and it's probably going to help if we try to choose the best tools. And that explains a bit our bias a bit for Rust from the beginning. However, we ended up with maintaining the system in Go, Tendermint, which I think it was originally written in Go. And I agreed with this. Actually, it was originally written in Go because it's actually much faster. I still think this is true. To prototype and to create from, let's say, bootstrap a project and quickly see, gain a sense, scope its complexity, get a sense of, is this valuable? Would people use this? How difficult it is to maintain? What are the right features? What are things we should trim down? So for the purpose of discovery and prototyping and so on, actually Go is an amazing tool. I guess this changes maybe with AI, but this definitely used to be the case for, I believe, at least between 2010 and 2020, 2022, I would say, or 2023 probably. So I think that was the reason why Go was chosen. I wasn't part of the team that initially wrote Tendermint in Go. It was started in 2013. So I think that was the choice. Because it was just quicker to prototype. It was, I think it was also a pretty hot language back then. I don't know in the history of Rust where it was in 2013, but it was probably a bit earlier than in terms of maturity compared to Go. Maybe I stand corrected there, you could tell me. And then to get into a bit more technical details, the system was written originally in Go, and it evolved a bit smoothly in the beginning, but then it became more and more tightly coupled, the different components or the different subsystems. So what Tendermint is supposed to do, the best analogy that I could use is a replicated database. So you could imagine just a MySQL cluster or PostgreSQL or so on. It is supposed to allow different machines to access the same identical strong read and write guarantees database. Basically, it's not exactly ACID style database. It's a bit different interface to it, because you, instead of inserting rows and reading rows and having this advanced SQL syntax that you could use to manipulate and filter your data, you are just creating blocks, and each block has a transaction, and a transaction sometimes can do arbitrary actions on the system, and then you have an application state. So you get user transactions, you shepherd them into a totally ordered sequence of blocks, and then each participant in the system applies that same total order of blocks onto their local state, and then what you end up is a technique called state machine replication. And that is the gist of why do you need consensus. You need consensus to reach agreement on this total order, and that is how you achieve a state machine replication by all participants in the system, as what Bitcoin does as well. All participants in the system ending up with the same application state, because they applied the same operations in the same order. And Tendermint was a fantastic tool to achieve that. But over time, I think I'm happy to stand corrected on this. I think it was written by not very advanced Go engineers. It ended up with hundreds of threads. So both memory and concurrency management was very, very difficult. You could not debug and you could not diagnose performance bottlenecks very, very easily, also because of that. And the overall architecture was extremely coupled, and concurrency model was with locks, so you needed to always share a lot of state. There was not much message passing, and whatever message passing was needed for the different subsystems to communicate in Tendermint was eventually was kind of mixed with locks, and it was just very, very difficult for that to be maintained. And that was the state of the database when we took it over. We actually did evolve it for roughly 2 years, and we were able to add features, but with extreme surgical precision. So imagine you take MySQL and you're not adding some new extreme support for new SQL syntax, but you're adding this small new RPC endpoint for you to query maybe how big is my database. It's a bit more advanced than that. But so we were able to evolve the database, but at a crawling pace, and that is because actually the system had undergone some changes in the past. So there was a previous team before us, and they attempted to change the code base. And the code then, when it was tested, put into production, or actually a testnet, they realized, this no longer performs, like it's no longer reliable. You have no predictability on how fast it takes to build a block. If we connect more than 50 peers together, they start randomly disconnecting. Basically, too many changes were introduced in the code base at once, and because the code base was so tightly coupled, it was impossible to diagnose. So we went back into the original version of the code base when we took it over, and we said, okay, we scratched these last 2 years of development, and we're going to try to add with surgical precision just the right exact narrow features that users just need right now, today. And that explains a bit why we couldn't go much further with that old code base. The old code base had certain kind of ossified design choices that were fundamental, and it was very difficult to evolve. It was also very mission critical, so you couldn't easily test it. It would have taken years. I went into a bit of detail, and I didn't really focus much on Rust, but so I did mention that we had a bias for Rust from the beginning. We were basically just waiting for the opportunity to implement something in Rust, and we were given a code base that was extremely complicated and difficult to maintain, expensive to maintain. And we realized, okay, this is the opportunity to rewrite it in Rust with a specific objective in mind, and that was, let's make it as flexible as possible, because we want the next iteration of this extremely complicated system. We want it to be evolvable and maintainable as cheaply as possible. And I think that explains, the different, let's say, rationale that went into the choice. First, a bias from the beginning, then the right opportunity, and Rust being also well known for its ability to be, it is amenable to writing systems that are extremely flexible, expressive as well, because you have a lot of access to different semantic constructs and syntactic constructs that allows you to build a code base that can evolve very smoothly.
Rust also seems like the language, or I would call it lingua franca of cryptocurrency companies and systems and things like that. I mean, C is still pretty much a kind of a proven technology for so many different industries. And also there's new languages like D, or I heard a lot about Zig in some different communities. So, I mean, have you actually tried to look at anything else before you went to go straight into Rust, or was it just like, this just makes sense, let's just go that route?
Well, we did have, like I said, we did have a bias for Rust. So we were mostly just looking for the right opportunity to use it. We did not explore any other languages before we decided Rust was the way. There is a lot of momentum, like you said, for Rust specifically in the blockchain industry at large. C is not used that broadly. I think Go is the winner in terms of infrastructure systems. So we did have this bias. The ecosystem needs it. We know many teams are very, very interested because of that. It has the performance angle as well. And all of this expressivity and flexibility and modularity angles that I already mentioned were important for us from the beginning. So all of this kind of coupled together, it was the momentum and the right conditions were just too appealing for us to resist. We didn't really investigate the other languages. I did play with other languages while I was in graduate school. Before I landed, I was thinking, okay, what is the best thing to build distributed systems? What is the best language? I tried Erlang, I tried Haskell, Scala. I tried briefly Rust, but I think it was the beginner experience for writing Rust distributed system is actually very difficult until you learn the ropes with the code, until you learn to love the compiler instead of the initial reactions, which are very, very, let's say, mixed feelings, or it's difficult to love the compiler in the beginning. I ended up landing on Go. That's why I said I have a pretty firm kind of agreement with the fact that Go is crazy good, or used to be crazy good at prototyping compared to Rust. And again, maybe that changes these days.
Well, I mean, it's funny that you mentioned this because I just recorded another interview recently with another company, and the interviewee said that actually I can't remember if he says as or even more productive with Rust than even Python, which I think is kind of interesting in terms of even prototyping, which is hard for me to understand because to me, in my experiences, is that writing Rust, I mean, I tend to not always use it, and it's usually because I can go faster without it. I mean, it's at least that's in my line of work. I find maybe it's because I don't work with it enough that it just becomes that easy. But he states that even with Python, he can somehow prototype faster with Rust, which is something that actually I remember some people who wrote some Rust materials about, and they said Rust is not good for prototyping because it has all these strong typing. So you're kind of also saying something similar. It sounds like where you can things have changed, right, since Rust a while ago to Rust now.
Yes, things have changed within Rust. Of course, it also has to do with individual taste and preference. And what I mean by that is, once I started uh, mm, spending more time with the compiler and with the language constructs and understanding what is it that it offers me, I became less comfortable with writing Python or Bash or Go as well. And by less comfortable, I mean I no longer have the confidence that what I write was right. I could have the confidence that it could run in some very hacky way, but I had this hesitation in myself whenever I still have it whenever I write Go now, that okay, this might not actually work, or this might actually just fail in a very, very unpredictable way. I'm always ready to be surprised by how it will not work. That's why I said it's good at prototyping, but and in terms of individual taste, I think once you get used to Rust, you just have a certain level of confidence, and if you're proficient enough, that confidence, even if it's a prototype, it's more important than moving potentially a bit faster, which Go could allow you, at the detriment of that lack of confidence that Go doesn't give you as Rust does. But all of this potentially might be even less important than using AI tools that help you do vibe coding, that you just give the prompts and you look at the code very briefly, and maybe you should do that more often, looking at the code and kind of testing it. But I think it's narrowed the gap between how fast you can prototype. Just given a person that has the same years of experience in Go and Rust, I think almost probably 95% of people who are in that situation, they are faster in Go, they are in Rust. It's just the way things are. But now that gap between how faster you could be in Go and then in Rust I think it has been closed, or it has been significantly either removed or alleviated. And the other thing, like I said, is the level of confidence that you have in the code that you just wrote. If you're just going to use it locally on some quick data, whatever, maybe Python or Go could work just as well. Though, I think that gap has been closing down.
Okay. Yeah, I mean that's interesting to hear. For because we're actually we talked about a couple different things, right? So and I also have some other material, right? So what you rewrote, you saw the okay. So you have Malachite, but I also hear this thing called Quint, and I see Quint was rewritten. Are they somehow related, or this is two different things in terms of your use of Rust?
There are two different things in terms of our use of Rust in informal systems. If you recall, when I mentioned that in 2019, when I met the other people that were part of Informal, that are still part of Informal, I was pitched this idea that we have two pillars. Okay, guys, this is it. We need to trust the systems that we're building. How do you foster this trust and reliability in these systems? Well, let's just do formal methods. Let's just verify everything, model checking, and Rust. And this is where Quint comes into play. In the first pillar of model checking, Quint is a language. It's actually a front end to TLA plus that is designed to be more appealing or more friendly to developers. If anyone is familiar with TLA plus, you may know that it has very, let's say, deep roots or foundations in mathematical set abstractions, mathematical thinking. So when Lamport invented it, he said, these are the right tools to help you think, to write models of your protocols and distributed algorithms before you implement or you write any line of code. You just sit down and you formalize them in terms of what are the acceptable behaviors, and that's the model. And those, then once you know what are those acceptable behaviors, how is your system safe, how is your system live, you do that using these mathematical constructs, and he encoded all of those constructs into the language called TLA+. But TLA Plus for developers is hell. I used it. I'm not a professional engineer. I'm not even any longer a researcher, I would say. But TLA Plus is very difficult to use because you're not writing a program as a functional code, or not even imperative or declarative code. You are writing a model which specifies the different possible behaviors of a system. And that's a completely different paradigm. You think you're writing a method or a function, or you think you're writing a data type, or you think you're writing some algebraic structure, but no, you're actually writing a model, and it's not even very easy for me to explain, to articulate what the difficulty is. And that explained why we invented Quint, which is just a front end to TLA+. So it translates into the same models in the backend that TLA+ is designed to capture. It's just that Quint offers this familiar developer-like, almost Rust-like interface to write your models. And Quint is written, I think most of the tooling in Quint was originally written in TypeScript. In particular, there's there's a parser because you write your model and then it needs to be parsed. There's a type checker and the simulator. The simulator is the one that actually, after you parse and you type check, you take the model and you say, does this model accomplish this safety property? So for instance, if a classic property in our domain is a user doesn't spend twice the same money. This is called the double spending problem. This is a classical property, and it's a safety property in the sense that the system should never allow that kind of behavior. So if I only have 50 francs in my bank account, I should never spend those 50 francs twice. I shouldn't convince you that I'm giving you 50 francs, and then in parallel go to my bakery on the corner and tell them, hey, here's 50 francs, give me 3 breads. So that's the double spending problem, and you can capture that, and the simulator would say, did the protocol that you just specify in terms of the behaviors of the protocol, in terms of the bank account, the different possible execution traces, the simulator will tell you, yes, what you just wrote does not break the safety property of what I call the double spending. So that's what Quint is, and that's what the simulator for Quint is, and that used to be written in TypeScript. And very recently, there was some feedback throughout the years that a simulator is a bottleneck, especially for developers. And this maybe wasn't obviously from the beginning that was the bottleneck, but when the team added this Visual Studio Code plugin to allow you to write, to have syntax highlighting for Quint and so on. We basically throughout the years made it more and more friendly to write models and protocol specifications. And from the bottleneck being, I'm not able to write anything in TLA+ because it's just so difficult, the bottleneck became, wow, now I'm writing code pretty fast because I have all of this tooling. The Quint interface, the syntax and the language is actually pretty friendly to developers. Then the bottleneck became, okay, now I want to test my code in much tighter iterations, and I want to get more confidence in faster, let's say, iterations. I want to look at some algorithm that someone maybe specified or a colleague is trying to test, and then I want to quickly write it and get some instant or almost instant feedback. Okay, did I write something that was good or not? In 2010 or something, when the main way to do that was through TLA+, and it was this clunky interface, you would potentially wait minutes or sometimes hours if you didn't write your property well, or the state that needed to be searched was too big. All of that to say that eventually the bottleneck became the simulator, and we realized, okay, this is actually a pretty good opportunity for us to write it in Rust. Just the specific part of the Quint tooling. I think the team did some experiments with other programming languages, given your question from earlier, whether before we jumped into Quint for Malachite. The answer to that would be for Quint, we did do, before jumping into Rust for Quint, I think there was some explorations into other possibilities, and basically Rust was chosen. Because of memory I think the 3 primary properties that motivated the choice. I'm not sure if this was captured in some kind of comprehensive table, but the 3 properties that we were looking for is what is the performance of simulations? Can we do them fast? What is how confident we are with the memory management, because simulations can take a lot of memory, and how expressive is the code base of the simulator, so that we make it friendly to contributors, so that you make it easily extensible, you make it easy to read, easy to maintain. So yeah, performance, memory management, and expressivity was among the things that motivated us to choose Rust for rewriting the Quint simulator in Rust.
I mean, I'm also kind of curious about, was the team? I mean, it sounds like you guys are definitely interested in it. Was the team already pretty familiar with Rust? Because I mean, Rust is, I mean, it looks easy, but then when you start writing with it, that the bar checker definitely kind of beats you into submission, right? So
Yeah,
were you guys
like,
already playing around with it or doing some small things before you did such a big rewrite?
yeah, we do have, like I said, we do have a bit of a bias for Rust in the company. Maybe a bit to, sometimes it is to our detriment, because you know, when you have a problem, you should just always try to pick the best tool for that problem. And sometimes Rust may not be that tool, but we do have quite a bit of expertise and yeah, a predilection towards simply choosing Rust because it's we trust it, and we feel very excited about the ecosystem, the builders around it. The teams building in Rust tend to be always very high quality and very well engaging with them. So we do have quite a bit of, let's say, love, or a love affair with Rust in general in informal systems.
Okay. When you have you ever done kind of benchmarking between the old one and the new one to see if it's gotten any faster, better in terms of resources or anything like that, or you just kind of changed it, felt better, felt easier to work with, and then that was the end of day?
There are some benchmarks, actually, yes. I think I couldn't speak expertly about the benchmarks because I wasn't part of the team that ran them. This is for Quint again. I'm not part of the team, but I am aware that they ran at least. I think they were exploring with 5 different approaches. I think some of them were not in Rust. I may be wrong, and they were benchmarking the different, let's say, key components of what it takes, or what is that could be bottlenecks in a simulator. For instance, how do you handle closures? How do you do just-in-time execution? I guess maybe other things as well. Again, I'm not an expert, so I think there was definitely some benchmarks, and there was definitely some data-based kind of intuition that we gathered before we jumped into this. It's also something that I think we've been wanting to do for like 3 years, to change the simulator. It's one of those things that you have 50 of these ideas, and they all sound good, and you don't know which one you should choose. Simulator was rewriting the simulator. Probably in Rust was one of those 50 ideas. And then when the opportunity came, just like with Malachite in Rust, we said, okay, let's let's do this. I think, yeah, the opportunity for Quint in rewriting in Rust might have been done in even more disciplined fashion than Malachite in Rust, because they definitely did more benchmarking than us with Malachite. And I also know that the team plans to do additional benchmarks as they are adding more and more functionality to the new to the prototype, basically, simulator in Rust. I think they only did parts of deserialization and parts of some evaluation, code evaluation, but there's a bunch of other parts left for the simulator, and I think with every step they are evaluating and benchmarking. I can tell you for the Malachite, which is the implementation of Tendermint, for the Malachite codebase, that's a bit different, but it's a bit different than Quint because what we rewrote in Rust is the core distributed consensus algorithm. And since this is a distributed algorithm, it requires a networking stack. And networking stack is not really the bread and butter of any infrastructure company these days. A networking stack is a solved problem, or at least that's what we like to think. So it's a bit different than the simulator for Quint, because there's this other key component that contributes to performance in very, very essential ways for Malachite. Nonetheless, we picked what we believed as a networking stack for Malachite in that being libp2p and gossip sub specifically in Rust. And we benchmarked it against the Go implementation. The Go implementation has its own networking stack. It would have been really cool if it had also the P2P networking stack. So then we could do the Go implementation of the distributed protocol with the Go P2P gossip sub versus the Rust distributed protocol implementation and the Rust gossip sub stack. And that would have been a really interesting comparison. We didn't do that because all the Go stack has its own native kind of built-in stack that is purpose-built versus the Rust rewrite, which is a lot more modular. So we can put almost any stack that we want underneath as long as we satisfy a couple of key properties that gossip sub to some degree satisfies. But to get to the performance angle, we run some experiments even without optimizing much gossip sub or even without investing key, let's say, optimizations or working on the networking stack that generally is an important part in distributed stacks. We got we were very happy with the performance comparison of the benchmarks between the Go. It seems like we're able to easily do 10x higher throughput in with the Rust-based stack with Malachite compared to the original Tendermint in Go version. So we're pretty happy about that.
Yeah, I mean, that makes sense. I mean, I remember looking up plain stuff in Go, and it felt like always the top question or top thing that would come up whenever I looked up anything in Go. I mean, this is not just looking up about Go, but this is when I was actually writing some Go or trying to find something like a library in Go. Like, it always felt like the top question asked was how to tweak the garbage collector, which is such an annoying problem. I don't think I've ever seen that many things in Java, even about GC and how that stuff works. I mean, did you also have some GC issues when you were using the Go implementation?
There were some. Actually, interestingly, the biggest problems with the garbage collector were not what is called the consensus engine, which was just the responsibility of the Tendermint in Go. The biggest garbage collection problem was the application on top of that. It is the application state, it is the execution of transactions. And that's where actually the biggest problem with garbage collection, because generally the state, you want to Merkleize it and you want to change it very often. So you have to be very careful about the efficiency of the type of, the trees or the other data types that you're going to employ. And it's generally pretty bulky. State is not just, it's like a database and it's an application state. And often the application state is accounts of people. And there's transactions that you apply to modify those accounts. And there's a lot of bookkeeping that needs to be kept, that needs to be taken care of. And yeah, the garbage collection was primarily the problem for the application level part of whatever stacks were built with Tendermint. In Go. For the Tendermint in Go itself, besides garbage collection, I would mention, I think I said it earlier, that the tight coupling and two on kind of wild or non-management of threads and basically Go routines and locks for concurrency control was just too much. They were all over the place. Too much state sharing was always led to very difficult problems to debug. When you try to relax a bit a lock, or you try to separate, to disaggregate, let's say, two parts of the system to make them not depend on one another as much, it's like whack-a-mole. It's just another problem appears somewhere else, and then you got to chase that. And then you realized, oh, actually that lock was needed, and we got to introduce it with the same coarse-grained granularity that it used to be originally, so we cannot get around that. Unless we introduce message passing. Okay, so let's introduce message passing, and then you introduce message passing, but you realized, okay, but this component actually cannot work with message passing because it depends on this 5 other subsystems, the RPC, the indexing subsystem, and so on. So you will need to revamp too much at once. And I would say those were, beside garbage collection, those were also pretty serious problems with the Tendermint in Go implementation. They still are today. But again, the system I would re-emphasize that the system actually acts very reliably in practice. It's just difficult to evolve and add and maintain. It's time-intensive and expensive. The usual kind of engineering pragmatic view that reading code is much harder than writing it really applies in this case. It's like one of the first kind of examples that I can give. It's also very similar to what happened. I think this is another famous example. And I think it was the rewriting of this early browser. What was it called? It's given the Netscape, maybe.
I think you're talking about when they wanted to open source it, right? The Netscape Navigator, which then became
Right. Yeah.
Firefox.
Yeah. They were trying to rewrite it, and it was a total failure. Realizing that that what we had originally was so reliable and so good, and to change it, we need to rewrite all of it. So let's rewrite all of it. And then they realized, okay, this doesn't solve any business problem. And okay, that was a bit different setup than ours, because in our case, we definitely want to make the system a lot more flexible and higher performance, and there is a clear demand for this in the industry.
Yeah, I mean, since we are here to talk about your use of Rust and with Malachite and everything, I mean, do you have a parting thought that we can end on?
What could be a good parting thought? I would say, just to emphasize that that the thing that gets us most excited, and the thing that let's say the property of systems that we care the most about, which is where there's the overlap with Rust, is the security to be able to foster trust in all of this extremely complex and extremely complicated and difficult to manage distributed systems such as blockchains. And this is what we try to specialize in the security and in the high reliability of such systems. And many times the right tool for this job is Rust. So I'm very happy with that. Thank you very much for the opportunity to chat here. We blog very often at Informal Systems about many of our challenges and the very cool findings that we have. And quite often they are related to Rust. That's another thing that we like to do besides just writing, just starting new investigations and explorations. And many times they have to do with Rust and documenting those online.
So if we search for Informal Systems, then we should definitely find your blog and everything where all your information is, right?
Exactly, yes. We also tend to be quite active on Twitter as well as a company. Personally, I'm also individually active on Twitter as well. And I also have my own blog where I sometimes write, but not so much about Rust, actually. More about distributed systems and sometimes personal things as well.
Okay. Well, Adi, it was great having you on and hearing about your rewrite with Rust and how much of a success it was. Hopefully we'll have you back on again, and maybe you'll have more stories about more rewriting, and then maybe I'll come out with a whole Rust stack, right? We'll see what happens.
Yeah, that would be brilliant. Thanks so much, Alan, for the opportunity. It was really fun chatting with you.
Yeah, thank you.